Okay, so good evening, everyone. Seems like more people won't be joining in, so maybe we can start. Today, we'll be discussing some questions in correspondence to what was taught in week 2 for the Linear Dynamical Systems course in NPTEL. So, this week, we'll be essentially dealing with subjects related to stability and given a linear LTI system. How do we go about determining whether the system is stable and the nature of its stability further, given the parameters that we usually have, like the state, like the system matrices and so on. Okay, so we'll start with a simple question. So in this question, we have to calculate the Frobenius norm and two norm of A. A is a 3 cross 3 matrix given as in here. So we want to find out the relation between these two, the Frobenius norm and the two norm. Okay, so first let us define what the two norms are. So the Frobenius norm is given by, okay, so this is kind of a generalization of the standard Euclidean norm in vector spaces, in normal Rn vector spaces, into the matrix space. So suppose I have a regular vector, let's say x equal to 1, 2, 3. What would be its Euclidean norm? Anyone care to guess? The uh, just a minute. Yeah. So yeah, we were discussing the relation between Frobenius and two norm for this particular matrix A. Yeah. So yeah, Aman, you were saying something about the norm of the normal Euclidean norm of this vector x. Okay, how do you get to this value? Okay, so let us first write out the definition, like the formula for the Euclidean norm. It is just xi square I equal to 1 to n. Right. So if we do it in this case, we have 1 square plus 2 square plus 3 square. So we'll have some 1, 4, 3, 9. So we'll have some root 14. Okay. So for this particular vector, we'll have the solution of root 14. Okay. Now, so as you can see, this formula for the Frobenius norm is nothing but the generalization of the formula that we had. Yeah, this formula for the standard n dimensional vector. And similarly, a norm which is termed as a two norm is defined for matrices as follows: maximum of root of lambda A transpose A. Okay, so what this lambda of A transpose A means is we want to find out the, like this entire expression means we want to find out the maximum among all eigenvalues of the matrix A transpose A, and like under the root. So usually we take A transpose A because most like a matrix need not be square. So A transpose A will ensure that it is square, and then we can obtain the eigenvalue of that matrix. But since we are kind of taking the quadratic term A transpose A, so eigenvalue of that, we then take the root of it and then choose the maximum amongst it. Okay, so then I want you guys to try this one out. We have the formulas for the Frobenius norm and the two norm. So I would like you guys to try it out and tell me which of these should be the answer. Maybe we can take some 3-4 minutes to do it, and then I'll have a poll. So problem one. Yeah, so please try out the question, then submit your answer via the poll. Okay, we can take some 3-4 minutes for that. Does any of you have come up with any answers? If so, you can submit it in the poll. We have four options: 1, 2, 3, 4. Can someone just confirm whether you can see the poll or not? Okay, thank you. Okay, we'll just wait for the others. Yeah, we'll just wait some more for the others to give their answers. Or maybe we can resume it. So I'm stopping the poll, or does anyone want any more time? Okay, then I'm ending the poll and we'll discuss the solution. Yeah, so let us first quickly just find out the Frobenius norm. So we just have to find out the root of the summation of squares of each element. So we basically have a root of 1 square is 1 plus 4 plus 0, 1 plus 1 plus 4 plus 4 plus 9 plus 1. Alright, so here you have 5, 6, 7, 11, 15, and 10. So this is root 25, so this is a nice 5. So the Frobenius norm of this matrix is 5. Now, so now we want to find out the two norm. So, but for that we need to find out the eigenvalues of this matrix. So, in fact, the eigenvalues of A transpose A. So, what is A transpose A? So, can you please answer if anyone has done this? Okay, let us just do it. Okay, thank you. Then, what were the eigenvalues of this? कोई बात नहीं. You can tell the answer. So, for finding the eigenvalues, we solve for this equation lambda I minus a. Its determinant has to be equal to 0. So if you put take this equation, then we can maybe move to MATLAB to check out. 1 minute. Yeah. Can you see the MATLAB screen? Yeah. Okay. We'll just clear this. Then we have this matrix given by A, right, which was 1, 2, 0, minus 1, 1, 2, minus 2, 3, 1, right? So first we'll run this. So we have this A matrix here. Now MATLAB has very nice functions norm where we can find out the norm of any matrix directly by just feeding it. So this gives us the norm of Frobenius norm of the matrix A, and writing only norm gives us by default the two norm. Okay, so first maybe we can do it step by step and let us find out the eigenvalues of this matrix. Okay, Okay. So if you look at it, the eigenvectors are these given by the V matrix, and the eigenvalues are given by these three complex values, right? And so what we will do is 18.74. I'm sorry. 1 minute. So these are the eigenvalues which we have. So what was the formula for the two norm? It was to find the maximum of root of these things. So basically we need to find the maximum of root of the mod of this thing, right? Because it's a complex value, so we can't directly take the maximum. So when you do that, what you'll find is these are the solutions. So for Frobenius norm, as we calculated, it was straightforward. The value is 5, but the 2 norm is 4.379. Alright, so I'll move back to the slides. Yeah. So here we had some lambda something something something, but the value was A2 is equal to, what is the value? Yeah, 4.379. 4.379. So AF we had was 5. So now which of these options seems to fit? AF is 5 and A2 is greater than equal to AF. That's incorrect. A2 is 5, which is incorrect. AF is 4.37, which is incorrect. So A2 is 4.37, which is correct. And A2 is less than equal to AF. So the correct answer is fourth one, right? I hope that is clear. Then we can move forward and find out. Let's move ahead to the next question. So I want to find out the eigenvalues of a negative definite matrix. So if one of you can tell me the definition of what a negative definite matrix is. Yeah, Amanda? Okay. Okay, I'll just define it for you. A real, positive, sorry, negative, definite, sorry, a real symmetric matrix A in the space Rn cross n is negative definite if and only if X transpose AX is strictly less than 0 for all possible vectors X in Rn. Okay, so this is the definition of a negative definite matrix. So take any real symmetric matrix. It is negative definite if and only if for all possible vectors in Rn X, this product X transpose AX is strictly less than 0. Now this is the definition for a real symmetric matrix, but similar definition can be extended to complex symmetric matrices as well. And there, instead of transpose, we'll have to take a conjugate transpose. So let's leave that aside for now. Now this is the definition of a negative definite matrix. So how do we then? So now we want to prove, like we want to find out what kind of eigenvalues will this matrix have. Okay. So how do we find out the eigenvalues? We take the determinant of this matrix, right? Lambda I minus A equal to 0. And the solutions of this equation will give me the eigenvalues. Let us just consider an example. A very simple example is this matrix. A is equal to the negative of the identity matrix. So let us find out the eigenvalues of this matrix. So let's take lambda I minus A is equal to, we have lambda plus 1, 0, 0, lambda plus 1. So what does this mean? Its determinant lambda I minus A equal to 0 will give us this equation. Lambda plus 1 whole square is equal to 0. So that means lambda equal to minus 1 and minus 1. These are the two solutions of the characteristic equation. So, so essentially, if this is, it happens to be that equivalent to this definition, there is another definition of negative definite matrix, which directly says that if the all the negative if all the eigenvalues of a real symmetric matrix are negative, then it is a negative definite matrix. I'm sorry I messed up earlier, but there is a proof for this. I'll update it in my slides later on. So for now, let us just accept that it is strictly negative. So the eigenvalues of a negative definite matrix are strictly negative. Okay, so with that I'll move forward. So for marginally stable homogeneous NTI system, the following statements are true. Okay, so can someone help me define what a marginally stable system is? Right. So that is one of the conditions. But essentially, by marginally stable, what we mean is, uh, first thing is it has to be Weibull stable, and second thing is, in some sense, like if you provide some input which is bounded, it cannot go unbounded or go unstable or things like that. It has to be constrained within some kind of neighborhood of the origin, like around zero, right? So if you have a asymptotically stable system or an exponentially stable system, what that means is if you're given some input, then the system will make sure that the output goes to zero asymptotically or exponentially as per the definition. So for marginally stable case, it just has to ensure that it will stay constricted within some bound neighborhood of the origin. So for that, a particular theorem tells us that a system is marginally stable if and only if it has Jordan blocks corresponding to purely imaginary eigenvalues of size 1 cross 1. So what does this mean? This means that when you diagonalize a system matrix, like let's say you have x dot equal to some ax, then you go ahead and let's say do some pz such that P inverse AP will now give us a diagonal matrix. So this diagonal matrix would typically consist along the diagonal elements, the eigenvalues of the system. Okay, but when we have repeated eigenvalues, what happens is, so let's say, I'm sorry, what did you say? Yes, yes, that's right. But like when you have repeated roots, what happens is you cannot find an independent eigenvector when you have repeated roots, and you cannot find an independent eigenvector for the number of roots. Like let's say you have a system A, and let's say this has 3, 3, and 4. So for this eigenvalue of 3, if you cannot find two independent eigenvectors, then you cannot decompose A into a perfectly diagonal matrix. Alright. So in that case, what we do is we find something known as the generalized eigenvector. Let's not go into that. And after finding the generalized eigenvector, we can find P matrix which is invertible, and the diagonal matrix that we get would be something of this sort. Okay, so here we have a Jordan block, but it is not of size 1 cross 1. It is of size more than 1. So essentially, a system is marginally stable if Jordan blocks corresponding to purely imaginary eigenvalues of size 1 cross 1. That is one of the options. And this happens only when the algebraic multiplicity of an eigenvalue lying in imaginary axis is 1. So what does this mean? It means that the so algebraic multiplicity of an eigenvalue is when you write this equation determinant of lambda I minus a equal to 0, and like in this, I believe, where was it? Yeah, let's take this example for like this for example. So the algebraic multiplicity of the eigenvalue lambda equal to minus 1 is 2. It essentially means the number of times it is repeated as a root in the characteristic polynomial. Okay, so if the algebraic multiplicity of an eigenvalue lying in imaginary axis is 1, that means it is repeated only once. So essentially, it does not have repeated roots on the imaginary axis. So when it has repeated roots, we know from classical control that it will become unstable, and this becomes as a result, like this in result gives that if this is greater than 1, then we won't have this as size of 1 cross 1. Alright. So algebraic multiplicity of eigenvalue has to be 1 for an imaginary axis eigenvalue, and correspondingly the Jordan blocks have to be also of size 1 cross 1. Only then a marginally, like a homogeneous LTI system will be marginally stable. Alright. So I hope this is clear. We'll then move forward. Yeah, 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 sure. सर ये आंसर क्या है? 1 होगा. अच्छा, तो ये वो न्यूमेरिकल टाइप क्वेश्चन था क्या? हाँ हाँ, इंटीजर इंटीजर टाइप था ना. हाँ, तो इंटीजर टाइप में आई थिंक 1 क्रॉस 1 लिखोगे तो वो इनपुट ठीक से एक्सेप्ट नहीं करता. तो लाइक 1 क्रॉस जॉर्डन ब्लॉक ऑलवेज स्क्वायर मैट्रिक्स होता है ना. जॉर्डन ब्लॉक इज ऑलवेज अ स्क्वायर मैट्रिक्स, स्क्वायर ब्लॉक. So instead of writing 1 cross 1, it can simply be given by 1, right? So I think that might have happened. If there is a problem with that, you can mail directly to the course coordinators, and I think they'll handle that. Yeah. So we are okay. Yeah. So now we move ahead to this question. For the LTI homogeneous system, homogeneous equation x dot equal to ax, this is A. Find out which type of system is this: marginally stable, asymptotically stable, neither marginally nor asymptotically stable, both marginally and asymptotically stable. Okay, so for this, what do we do? Simply, we first need to find out the determinant of this thing. Yeah, eigenvalues of this thing. So, determinant of lambda I minus a equal to 0. So, what do we have here? Determinant of lambda plus 1, 0, minus 1, lambda 0, 0, 0, minus 1 equal to 0. So maybe you guys can try this for a couple of minutes, then we'll discuss. So once you have solved, kindly put the solution of this on the chat box, like whatever eigenvalues you found out, then we'll proceed. Yes, that's it. So we can directly just find the determinant. It is given by, okay. So this is the characteristic polynomial is equal to 0. Okay, so we have two repeated roots 0 and one negative root minus 1. So, okay, tell me, when is a system asymptotically stable? When is this system asymptotically stable? Yeah. So in terms of eigenvalues, what result do we know about asymptotic stability? Okay. So there is a result, which is a theorem. So essentially, a system, like a system of this form, LTI and whatever we know, these kinds of systems, they are asymptotically stable when, if and only if, all eigenvalues are strictly negative. Okay. So from the previous question, what does this mean? From this question, in fact, it means that a system is asymptotically stable if and only if this matrix A is negative definite. Alright. So if we have one eigenvalue is equal to 0, like the real part of eigenvalues are strictly negative. So if we have that one part of like one particular eigenvalue is, let's say, 0, then one thing we can be sure is it won't be asymptotically stable. At best, it will be marginally stable. Now, further, if we have repeated roots on the imaginary axis, then as we saw earlier, it will give us that the system is unstable. So in this case also, we have two roots at 0 and one root at -1. So that means the system is neither marginally stable nor asymptotically stable. Is it clear? Okay. So with that, we'll move ahead. So for the LTI homogeneous system given by this matrix, which is the same as the previous one, find out its characteristic polynomial. So the thing, okay, this we have already found out here. This thing itself is the characteristic polynomial lambda square into lambda plus 1. So this is the correct option. Okay. I hope it is clear up till this point. Okay. Okay. Then we have, given the following homogeneous LTI system, this one. X dot equal to Ax with A given as this, then the following statements is or are true about the equation. So we say that, okay, we have this A matrix, alright, and we say that this A transpose P plus PA is the negative of identity. This equation is satisfied for what kind of P? That is what we want to find out, okay. So first, let us forget everything and just find out the eigenvalues of this matrix. Maybe we can try that for a couple of minutes. Once you find out the eigenvalues, let me know the answer in the chat box. Yeah. So let me know when you have found out the eigenvalues in the chat box, please. So, Aman, have you found out the answer? Is that what you are saying? Okay. Okay, so you are saying one. Okay, let's just find out. We'll have lambda. Here we'll have minus 1, lambda plus 1. Okay, determinant is equal to 0. So that gives us lambda square plus lambda plus 1 equal to 0. So this solution is there at root of, no, this will be j root 3 by 2. Yeah, so that is correct. We have minus half plus minus j root 3 by 2. I think, Amin, you made a mistake at this point. I think you probably considered this as minus, and hence you got this answer minus 1 minus root 5 by 2. Okay, so we have this as the eigenvalues. Okay, no, so based on the previous question about the stability of a system from its eigenvalues, we know that this system is now asymptotically stable. Why? Because the eigenvalues has negative real parts. Okay, strictly negative. There is no eigenvalue with a zero real part. Asymptotically stable. Okay, so then let us move to the question at hand. So we say then we want to find out something about this matrix P when it satisfies this particular equation. Let us find out. A transpose P plus PA is equal to minus I. So let P be some matrix of the form P1, P2, P3, P4. Okay. So we know A. We can write A transpose 0, 1, minus 1, minus 1. Then we have P here, P1, P2, P3, P4, right? Plus, okay, let us take one assumption on P where it is a symmetric matrix. Okay. Let us have this P1, P2, P2, P3, okay, and into A 0, 1 minus 1 minus 1 equal to minus of 1, 0, 0. Okay, let us solve this. So if you multiply all the matrices, what you'll essentially get is one matrix on the left hand side equal to this matrix on the right hand side. So here you'll have some terms, like some expressions in terms of pi, some p1, p2, p3. Okay. So then you basically have a system of linear equations. That's all. So let us find the values for p through this. Yes, minus 2. Sorry, what is the p you get? P is equal to. Okay, you are saying this about this matrix? Okay, 1 minute. So this is minus 2p2, uh, p1 minus p2 minus p3. Yeah, p1 minus p2 minus p3. Yeah, p2 minus 2p3. Okay, so from this we have essentially three equations, right? Because these two are same and this two are same. So obviously this minus 2p2 equal to minus 1 is one equation. This equal to this is one equation and this equal to this is one equation. Alright. So I'll add another page. 1 minute. We have minus 2. 2p2 is 1. Then p1 minus p2 minus p3 is 0. And 2p3 minus p2 is 1, right? So this gives us P2 is zero point 0.5. From there we can find that P3 is what? 1, yeah, 3 by 4. And uh, what do we have? Then further we can find P1 from this as P2 plus P3, which is 1 by 2 plus 3 by 4. Is it correct? Let me just check these equations. We have minus P2 here. So minus 2P2, right? Then here we have minus P3 plus P1 minus P2, correct? Then here P1 minus P2, P2 and minus P3, P1 minus, correct? And here P2 minus P3 plus P2. I think we'll have 2 P2 here. Can you just check once? We'll multiply this with this and this with this. P2 minus P3 plus P2 minus P3. Can you just confirm once if we'll get 2p2 minus 2p3 here? Yeah, sure. Yeah. Okay. Just a minute. Yeah. Okay. So then we have a change in equation. So here we have two, right? So we got P2 equal to zero point 0.5 from this. So from here we'll have P3 equal to 1 plus 2P21. Sorry, minus 1. Yeah, I took the negative 2P3 minus 2P2. So 2P2 minus 2P3 is equal to minus 1 can be written as 2P3 minus 2P2 equal to 1, which I have written here. So this gives me P3 equal to 1 plus 2P2 by 2. So that is 0.5 plus P2 0.5, which is 1. Okay, and P1 is equal to P2 plus P3, which is 1.5. So P is 1.5, P2 was zero point 0.5, zero point 0.5, and 1. Alright, so so from if this is a system and we showed that this system is asymptotically stable, then for such a system, for such a matrix A, there is a result which says that I'll write the result. Give me 1 minute. Yeah, so there is a result, in fact, which says theorem that A is asymptotically stable if and only if for every symmetric matrix Q, for every positive definite matrix Q, there exists a unique P such that A transpose P plus PA is equal to minus Q and P is equal to P transpose and it is positive definite. Okay, so I'll just tell what the results is. So we have a system, let's say x dot equal to ax, which happens to be asymptotically stable. All right. So we have an asymptotically stable system. So the theorem says this condition is equivalent to saying that for all positive definite matrices Q, there always exists a unique positive definite matrix P such that this particular equation is satisfied, this equation. Okay, so in this situation, we had a system x dot equal to ax with some a. We had found out that this a has eigenvalues with only negative real parts. So that means it is an asymptotically stable system as per previous results. So now from this statement, what we can say is since the system is asymptotically stable, for all positive definite matrices Q, there exists a unique P such that this A transpose plus P plus PA is equal to minus Q is like A transpose P plus PA will equal minus Q with P being a symmetric positive definite matrix. So here we say like then the following statements is are true about the equation. Since this equation is true with like A is asymptotically stable and I is here the Q matrix, right? So I is a positive definite matrix. So and we know that for all positive definite matrices Q, this result holds. So definitely it will hold for a particular positive definite matrix, namely the identity matrix. So what we can say is there exists a unique P such that this is true. So for this, we'll have the solution is matrix is unique and P is symmetric and positive definite. Right. So by the process that we have solved for P, we just assume that it is a symmetric matrix, and after that we could solve all the equations and we obtained the value of P. So obviously it is unique because there cannot be another P which will satisfy this set of equations, because we could, like, we did not have a condition where singularity or something came and we had infinitely many solutions. So we'll have only one unique solution. And further, if you find the eigenvalues of this, it will be equal to, like, it will be like this matrix itself will be positive definite. All right, just give me a minute. Yeah, so I'll show you the MATLAB code. Mm, I'll share my screen here. Yeah, I hope you can see my MATLAB screen. So, so we had this matrix A, 0, 1, minus 1, minus 1. All right. Now we'll use a function namely liap. Okay, I'll tell you liap. I'll show you what it is. Um, okay, I'll show this to you then. Yeah, I hope you can see this documentation now. So liap is a function predefined in MATLAB. All right. So this gives us the solution. Liap solves the special and general forms of the Lyapunov equation. That is x equal to, so the solution of this Liap a comma q, x whatever it might be, solves the Lyapunov equation ax plus x a transpose plus q equal to 0. Alright, so for us, we want to solve A transpose X plus XA plus identity equal to 0. Alright, so into this function, we will just plug in. Yeah, I'll also put it here. Okay, so we want to solve A transpose P plus PA equal to minus I, or in the sense A transpose P plus PA equal plus I equal to 0. But this particular function solves AP plus PA transpose plus I equal to 0. Alright. So here we'll just have to feed in A transpose instead of the standard A. So P is equal to Lyapunov of A transpose comma identity of size 2. That will give us the solution of P. So I'll just solve this. So P is equal to 1.5, 0.5, 0.5, 1. That is also what we got. And further, if you evaluate this term, A transpose P plus PA, you see that it turns out to be exactly minus of identity. Alright, so we can verify through this that the particular P that we found out, it satisfies the equation and it will be unique. And okay, one more thing we have to verify. It is, let us find out the eigenvalues of P. P command D. Question 6. Yeah. So you see the eigenvalues, they are strictly positive. So that means that the matrix P is a positive definite matrix. All right. So is this clear, whatever I told till now? Is there any doubt regarding this? Okay. Okay. Now we'll go back to this. Okay. Now we'll move ahead to another question. For the discrete time system given in this, with x of 0 is equal to some initial starting condition and a is given, we just have to find out the value of x of 2. So this is pretty straightforward. Can someone give the answer? Or at least first let me know what the procedure for such a problem is. Okay, okay. So what you are saying is I'll take k equal to 1, right? So that from this equation, what can I get? X of 2, because k is equal to 1, so 1 plus 1, 2, is equal to a x of 1, right? But do I have the value for a x of 1? Yeah. So now I'll set k equal to 0. There I'll have x of 1 is equal to a into x of 0. So what does it mean? X of 2 is equal to what? In terms of x of 0, what can I write? Right. Okay, let us do that. So try it out for 2-3 minutes, then we'll discuss. Yeah. Yes. Option number one, is it? Yes, have you tried it out? So Aman says the answer is one. Do you have any other option? Any other solution? Okay, let us just solve it. So x of 1 is a into x of 0, right? So here we have 1, 3. Is this correct? Okay, then we want x of 2 equal to 1, 0, 2 minus 1, 1, 3. Now what is this? This is 1, 2 minus 3 minus 1. So that's correct. But what if I asked you x of 10? How would you do it? Yes, but how can we boil, like here we have, here since k equal to 2, we want to find out x of 2, we need to kind of solve in two steps, k equal to 1 and k equal to 0. So for any general k, we'll need to solve for k steps, right? But how can I combine all these k steps to get a single equation that will directly give me x of k in terms of x of 0? So, okay. Let us think of it this way. I have x of k plus 1 equal to a of x of k, right? Then that means x of 1 is equal to a x of 0. So let's just put it this way. X1 equal to a x naught, but x2 is equal to a x1. But what was x1? Yeah. So this is a x naught. So this is a square x naught. Similarly, if I write x3, it is a x2, but a cube x naught, right? So likewise, we can just write xk for any k is 8 power k x naught. So this provides, even though we need to find the like power of kth power of a, but still this kind of succinctly describes the entire process into one equation. Okay. So let us just confirm what is a square. We can find out 10 into 1 to 1. Is this correct? Yeah, sure. Yeah. So this is clearly the identity, and identity into x naught will just be x naught. So that is why we got this as the answer. Okay, let's just check once in MATLAB. And what happened? Okay, we were in question 7. Right? Yeah. So we had the matrix A 1, 0 and 2 minus 1, and this is the initial condition. So x2, okay, first let us find out x1 is equal to A into x naught. So what was x1 we had found out? It was precisely 1, 3, and now x2 can either be A into x1 or it can directly be a square into x naught, right? So this we have verified. Any issues with this one? Any issues? Okay, we'll move forward. So then we move ahead to another question. The impulse response of two LTI systems are given by these two. This is the first impulse response. This is the second system's impulse response. Which of the following statements is true? So can someone define what is Weber stability? Right. So this is bounded input, bounded output. So if we apply any bounded input, then we'll always get a bounded output. But now, how do we check whether for some impulse response h of t, the system is Bibo stable or not? Oh, yeah? Okay. So this is the condition for Bibo stability, 0 to infinity, h of t dt. It has to be finite. So if this thing is finite, so essentially you can think of it this way, that you have an impulse response And if you provided a bounded input, then you would be convoluting it with that u of t, dt 0 to infinity, and then this had to be bounded. Okay, so then you can show that, like, you can find this result in any standard control systems textbook, Norman Nice, for example. You can show, like, you can find the result that shows that, like, the bounded input, bounded output stability is equivalent to this condition. That is, if you show that the integration of the impulse response from 0 to infinity is finite, then the system will have to be Weibull stable. Okay, so let us first check for g1 of t. I want to find out 1 by t plus 1 dt 0 to infinity. Can someone help me with this? Standard integration. Yeah. ln, will it be only t or t plus 1? Yeah, ln t plus 1. Oh, sure. So it will be 0 to infinity. Right, so this is what, is it finite? It won't be finite. So it is infinite. So what does this mean? This g1 of t is not Weibull stable. Right. Then let us check for g2 of t. So I want to find out this. How do I do that? Yeah. So tell me. Yeah, yeah, yeah. Yes. Yeah. E to the power minus t bracket minus t minus, right, 0 to infinity. Let's just do the steps for public clarity. So this will apply by parts. So we'll have it for minus t dt minus dt by dt e to the minus t dt. So here we'll have minus t e to the minus t minus 1 to minus e to the minus t dt. That is minus t e to the minus t minus e to the minus t. So which gives us this. So from 0 to infinity. At 0, so this is essentially 1 plus t e to the power minus t infinity to 0. At 0, what do we have? 1 minus, yeah. At infinity, yeah, but be careful. At infinity, you have to show that limit t goes to infinity, t, this entire thing 1 plus t e to the power minus t is equal to 0. Right, so for that, you can just check that 1 plus t by e to the power t, limit t goes to infinity, and you know that e to the power t has a series expansion of the form, yeah. So clearly the denominator has a greater order than the numerator, so this will simply be 0. So this is 1 minus 0, this is 1, so this is finite. So the solution is that G2 is, only G2 is Weibull stable. Yeah, is it clear? Okay, so then we move forward. Choose the correct statement for an LTI system. If the system is exponentially stable, then it must be Weibull stable. Okay, so what is your reasoning for telling this? Right, Right. So exponentially stable means that the output, yeah, drops down under an exponential envelope. So obviously that means if you give an bounded input, then obviously the output will be bounded because it in fact goes to zero. So exponential stability is a much stronger result than Weaver stability, right? So if a system is exponentially stable, then it must be Weaver stable. Then what about if the system is okay, this is clearly wrong. And then if the system is Weaver stable, it is always exponentially stable. Is this relation correct? No. Give me a counter example for this. हाँ, but इसके लिए एक example बोलो. Like an example of a system that is Weaver stable, but it is not exponentially stable. Okay, let us consider a very simple, just what do we say? Identity system, right? So I given some input, output is also X. So clearly this system is Weaver stable. So linearly decreasing to zero system. What do you mean by this? I couldn't understand. Linearly decreasing to zero means? Not exponentially. Okay. Yeah. So you can consider systems like that. But in a linear system context, if you have strictly negative eigenvalues, then the system is both asymptotically as well as exponentially stable. So for linear systems, we cannot consider a system of that form. So we'll have to go into the nonlinear systems domain. So let us just consider this simple example. Let's say I have the identity system. So any input X gives me an output X. So clearly this is bounded input, bounded stable because the input and output are equal. So if the input is bounded, then obviously the output will be bounded. But is it exponentially stable? No. Because let's say I give an sine input, then the output is also sine input, sine. It won't go to zero exponentially, right? So clearly, if the system is Weaver stable, it need not be exponentially stable, right? Then we move on to the final question of the day. So given x dot is some ax plus some bu, y is equal to cx, obtain the expression for the system's impulse response. So how do we do this? So in regular control systems, how do you obtain the impulse response? Yeah, that's true. Delta of t you apply to the system, it will give me the impulse response h of t. But there is another relation with the impulse response. If you take the Laplace transform of this, then h of s is the transfer function of the system. Is it not? So, yeah. So, if so essentially we can obtain the system's impulse response as the inverse Laplace of the transfer function of the system. Alright. So x dot equal to ax plus bu and y equal to cx. So what is the transfer function of the system? Yes, yes, right. Then how do we get it? X of 0. So remember that when we talk about transfer function and the like, we consider zero initial conditions. So here we'll have Si minus A into Xs is equal to B US, right? This implies Xs is Si minus A inverse US. Sorry, B US. Yeah, B US. And Y of S is equal to C into Xs, which is Si minus A inverse B into U of S. So the transfer function is nothing but Y of S by U of S. So it is C Si minus A inverse B. So let's find this. We have A is given here, B, C. So let's first find out Si minus A inverse. What is this? S minus 1, minus 2, 1, S minus 3 inverse. Tell me what is this? Yeah, please. Yes. Plus 2, minus 2. And divided by, so this is S square minus 4S plus 5. Okay. So then C into Si minus A inverse into B. What is this? Tell me the value of this thing. Hmm? S minus 4. Correct. Okay. So tell me what is the Laplace inverse of this transfer function? Yes. So let's wait for others as well and put the answer in the chat box. Yes. Okay. S determinant is S minus 3 into S minus 1, right? Plus 2. Correct? So S square minus 3S minus S plus 3 plus 2. Is it wrong in here? Okay, okay, no issues. Yes. Yeah, no, no issues, no issues. Yes. E to the power minus 2t cos t 670. Okay, let's check what is the answer. So we have s minus 4 by s square minus 4s plus 5. Right. So we can write this as s minus 4 by s minus 2 whole square plus 1, which is 1 square. Correct? So this is s minus 2 by s minus 2 whole square plus 1 minus 2 into plus 1. So we know that s by s square plus 1 is cos t and 1 by s square plus 1 is sin t. But here we have a frequency shift, so we'll have a exponential time term. So Laplace inverse gives us e to the power 2t cos t minus 2 into e to the power 2t sin t. So we'll have e to the power 2t cos t minus sin t, 2 sin t. Correct? Yeah. Okay, so any doubts up to this point? Okay. Then there is another way in which we can find the system's impulse response. That is via directly taking the solution of this LTI system. So can someone tell me the formula for the solution x of t? Huh. But in terms of LTI, like what is phi? 80. So we have it were 80 x naught plus, so 0 to t it were a t minus tau b root of d tau. Right. So yes, go ahead. Uh, So u of tau, we have to take delta of tau. Right. So delta of tau is in integration means the integral will only, so integration sum f of t del of t dt minus infinity to infinity is just f of 0, right? So this happens because delta of t has value only at t equal to 0, right? So this is kind of the functional definition of an impulse. So it has value only at t equal to 0. Everywhere else it is 0. And at t equal to 0, the magnitude is such that delta t minus infinity to infinity dt is 1. So basically the area under the impulse response curve is 1 plus 1, but it is pointed only at a particular 0 value, right? So when you take any integration of this form, we just get f of 0. So x of t can be written as e to the power at x naught plus e to the power at into e to the power minus a tau b at a value of tau equal to 0, correct? So this we have e to the power at x naught plus b. Yes. हाँ, एक मिनट। कहाँ तक समझा था? यहाँ तक? Okay, okay. So we had e to the power at x naught, correct? Then we had some function f of tau into delta of tau, right? Some 0 to some t. So we saw that if we have an impulse function and we are taking an integration, then only at 0 value we just get f of 0. So this entire integration is just f of 0, right? So this entire integration will also be f of 0, where f is this function, f, right? So this is f and we are taking a tau equal to 0. Is it clear? Yeah. So this means e to the power at x naught plus b is the impulse response, is the state, is the x of t when you provide u of t equal to del t. Okay. So what is y of t? It is just c into x of t, which is c into e to the power at into x naught plus b. Okay. So what different, how is this solution different from the one we obtained previously? That is, previously we found out the Laplace inverse of the transfer function h of s. Alright. And now what we are doing is we found directly the solution through state space methods and then found out the impulse response y of t is equal to c e to the power at x naught plus b. How are these two different? Okay. So h of s, remember that while finding h of s, what we did was we took sxs minus x naught is equal to we had a xs plus b us. So if we don't eliminate x naught, then we'll have si minus a x of s equal to x naught plus b u of s, right? If u equal to delta, then this is just 1 because the Laplace transform of impulse response, Laplace transform of impulse response is equal to 1. Then we have x of s equal to si minus a inverse x naught plus b. Y of s equal to c x of s. So y of s equal to c si minus a inverse x naught plus b, right? So this and this. They are the exact same thing. Like when you take the Laplace inverse, because e to the power at is just the Laplace inverse of Si minus A inverse. So essentially, here we showed the same solution through two ways. One way is you can directly go through you can take transfer function and then find its inverse. That will give us the impulse response. Also, you can directly solve the state space differential equation and get the solution for the output, which will also give us the impulse response. Is it clear? Okay. So, are there any other doubts? Okay. So, with that, then we'll stop for today. So, yeah, I'll also be uploading the MATLAB codes for each of these questions, and you guys can go through it. Yeah, no issues. Thank you for attending class.